Okay, we're continuing with Chapter 5 in the statistics textbook. In this video, we're going to go through section 5.5, which is on percentiles and the normal curve. So in the previous video, we talked about percentiles. And what we discussed was that if you've got a histogram or a list of numbers, same thing, and the distribution of that list of numbers, the distribution of the histogram, closely follows the shape of the normal curve, or is, you can say it's, you can assume that that data is normally distributed, then in that case, very good summary statistics for that data are the average and the standard deviation. However, if you can't assume that the data is normally distributed, then in those cases, the average and the standard deviation are poor summary statistics. So instead, what statisticians often use in those cases as summary statistics, descriptive statistics, is percentiles. Okay, and we went into specifics on what a percentile is, how to calculate it, how to interpret it, all in the previous video. However, it's not like if the data is normally distributed, then you can't use percentiles. You can apply percentiles to normally distributed data as well, just like you could calculate the average and standard deviation for non-normally distributed data. So that's what we're going to do in this video. We're going to talk about percentiles and the normal curve, or normally distributed data. When a histogram does follow the normal curve, the table can be used to estimate its percentiles. The method is indicated by example. So they're saying the table, what do they mean? Well, to calculate a percentile, we're going to be finding what position along the horizontal axis corresponds to a certain percentage of area to the left of a vertical line drawn at that position on the horizontal axis. It's the exact same concept as what we learned in the last video. You just apply it to a normal distribution. And so to calculate areas in the textbook, they use the graphical method, but we just use the actual formula with the graphing calculator. So that's what we're going to do here. And so just like we've done in the previous videos multiple times, I put this formula here for the normal curve into the graphing calculator and saved it as equation E. So there it is. They take the 100 over square root of 2 pi and put it as 50 square root of 2 over square root of pi, but it's the same formula. Okay, among all applicants to a certain university one year, the math SAT scores averaged 535, the standard deviation was 100, and the scores followed the normal curve. Estimate the 95th percentile of the score distribution. All right, so how do we do this? Well, first of all, you need to understand what 95th percentile means. Is this a percent? The 95th percentile, is that a percent? Absolutely not. The 95th percentile is whatever the horizontal units of the histogram that you're referring to are. So it would be a certain SAT score. That would be the 95th percentile. It's the SAT score that when you draw a vertical line from the horizontal axis of that score upward, then the area of the histogram to the left of that line is 95% of the total area of the histogram, so in other words, 95% of all of the applicants were at or below that score. But okay, it's saying that this data here, this list of scores followed the normal curve. So how can we use that to find the score that represents the 95th percentile? Well, a couple of videos ago, we worked example problems on calculating the area under the normal curve. We saw how we can go in reverse. If we have an area that we know on the normal curve, we can use that to calculate what z-score that corresponds to. That's what we need to do here. So what we need to do is, let's first get the definite integral of this equation E with respect to x. It's going to go from some number, I'll call it z. So that's the upper limit. The lower limit is negative infinity. Right? That's the entire area to the left of this z here, the z being the standard units. Okay? Now we want to go to algebra, solve, and then this is going to be equal to 95. And we want to solve for z. There you go. So 1.64 is the Z value. Is that the final answer? Is that the SAT score? No, that's the SAT score we're looking for in standard units. We just need to convert that from standard units to the SAT score, and that's the answer. So the Z score of the SAT score we're looking for is 1.64. How do we convert that from standard units back to the actual score? Well, what does this mean? This is how many standard deviations that score is away from the average. It's 1.64 standard deviations above the average. The standard deviation is 100, so it's 164 units above 535. What's 535 plus 164? $6.99. Okay. There you go. They go through the whole process and they get 700. What we got was more accurate because they got a Z of 1.65. We got 1.64. I would 60, but that's because they're using the approximations of the table. I would say 699 is more accurate. But yeah, the idea is if you scored in the 95th percentile, that means 95% of everyone that took the test scored lower than you. 95% of the people that took the test, you scored higher than. Okay, so you see, percentiles apply to normally distributed data as well. And it works very well if you want to use that as a descriptive statistic, especially when it comes to test scores, right? It makes sense to say that someone scored in this percentile. So the average and the standard deviation are very good descriptive statistics of normally distributed data, but so can percentiles can be as well. It's just in a lot of cases, the average and the standard deviation don't work very well for data that's not normally distributed. The terminology is a little confusing. A percentile is a score. In example 10, the 95th percentile is a score of 700, right? A percentile is it's a score, or it's whatever is the horizontal axis, or the units of the horizontal axis of a histogram, the units of the data points. That's what a percentile is. So the terminology is confusing. A percentile rank, however, is a percent. If you score 700, your percentile rank is 95%. There's even a third way to say the same thing. A score of 700 puts you at the 95th percentile of the score distribution. Okay, so if someone says percentile rank, then they're referring to the percent. There's another term. And here's another type of sentence that you might hear. It says, so a score of 700 puts you at the 95th percentile of the score distribution. So all of these different terms could be thrown around. All right, let's work these three problems here. At the university in example 10, one applicant scored 750 on the math SAT. She was at the what percentile of the score distribution? How do we determine this? Well, we know that we can assume this list of SAT scores is normally distributed. So in that case, since we can easily find areas under a normal curve, then all we need to do is convert this score to standard units and find the area under the normal curve. So that's to the left of this number in standard units. Okay, so how far above the average is 750? The average is 535. So 215 above the average, and how many standard deviations is that? 100 is the standard deviation. So 2.15. Okay, so now we need to find the area under the normal curve that's to the left of 2.15. That's easy. We just put here 2.15. So 98%, we'll call it. You're in the 98%. If you scored 750, then you're in the 98th percentile. For the university in example 10, estimate the 80th percentile of the math SAT scores. Okay, this is exactly what we did with example 10. Just now it's going to be the 80th percentile. So what SAT score? Well, no, okay, we need to first determine what z-score corresponds to having to the left of that score, there's 80% of the area of the normal curve. Because again, this data we're assuming is normally distributed. Okay? So what we do is we come here and put 80. So the z-score is 0.842. All right, so now we just need to convert this to a SAT score. This is the SAT score we're looking for. It's the 80th percentile. And they're saying estimate here because we're assuming that the data, that the SAT scores are normally distributed. The data doesn't technically exactly follow a normal distribution, but it follows it closely. So everything is, from that standpoint, everything is technically an estimate. All right, so the SAT score we're looking for is 0.842 standard deviations above the average. So a standard deviation is 100, so 84.2. 100 times 0.842 is 84.2. So what was the average? 535. So 535 plus 84.2, 619. So the 80th percentile is a score of 619, right? That's kind of the terminology is confusing. The 80th percentile is a score, an SAT score. Now the back of the book says the answer is 620, but we use the exact formula, so it's more accurate. I mean, unless you actually, I take that back, because if someone scored in the 80th percentile, then they need to have a score that's greater than or equal to this. So 619, technically you'd be like in the 79th point something percentile. So I guess you would put 620. I'm just saying that this is, the way we're doing it is more accurate than the graphical method. So I guess you would put 620. If you want to say you're truly in the 80th percentile, not the 79.8 percentile, you'd put 620. For Berkeley freshmen, the average GPA is around 3.0. The standard deviation is about 0.5. The histogram follows the normal curve. Okay, so this, you're assuming that for Berkeley freshmen, you have the histogram, and you look at the histogram, and it closely follows the normal curve, so you can assume it's normally distributed. But I guess, again, we talked about this. If you have the histogram, then you can actually get the literal 30th percentile from the histogram you have, right? So you would, why would you even use the normal curve? Just use the, use the data you have, the actual data you have. But this is just, we're just doing exercises to get used to the idea of assuming a normal distribution, because when we get to future chapters, we're going to be doing that a lot. We're not going to have the data, the actual, the data. We're not going to have the actual histogram, so we're going to have to assume a normal distribution. But it's too advanced to actually give real examples here about, how we have data that how we don't have the actual data. So they're just giving these more trivial examples here where for Berkeley freshmen, we have the data, but we're still going to, for some reason, assume that it's normally distributed instead of using the actual histogram. This is just an exercise, okay? So again, for Berkeley freshmen, the average GPA is 3.0. The standard deviation is 0.5. Assuming that histogram, that data is distributed normally, meaning the histogram for that list of GPAs follows the normal curve, estimate the 30th percentile. So we're looking for a GPA, right? We're looking for a GPA. So if we're assuming the data is distributed normally, the 30th percentile is going to be when we think about the normal curve, it's going to be a z-score to where if you draw a vertical line at that z-score, 30% of the area of the normal curve is to the left. So how do we find that z-score? We just come here and we change this to 30. So that z-score is minus 0.524. So that score is to the left of 0 for the normal curve, right? That makes sense. Because if you're the 50th percentile, you're at 0. Anything above 50 percentile, the z is going to be above 0. Anything less than 50, the z is going to be less than 0. Okay, so how many standard deviations, something that's 0.524 standard deviations below the average? What GPA is that? Okay, well, a standard deviation is 0.5. Okay, so this is like 1.0 something standard deviations, right? So we've got this score we're looking for. Well, no, we've got this deviation from the average. So it's this score we're looking for minus the average, which is 3, and then divided by the standard deviation is going to equal to minus 0.524, right? So minus 0.524 times 0.5, x minus 3 is equal to this, so add 3 to this, 2.74. There you go. That's the 30th percentile.